Right, start recording. We're live.
Hi, future me.
Hi, future me. You're going to hear that one day. All right, characteristics of gases. What tells you that it's a gas? What can you identify? Oh, I love that. We'll start with what she says. Yes, you're right. Yes, both of you. Okay, let's start out. She said there's no shape. Okay, and shape is just what's the fancy word for saying shape in science? It has no defined what?
Definition.
Volume. Okay. No defined definition is not the right answer. All right. One thing that you definitely know about gases is that there's no defined volume. Okay, and the reason is because there's so much space between the particles that you can't really tell what they take up because each particle is so far away from the next particle. So there's not a defined volume. Those particles are just spread out. What do you also know about gases? Love it. Okay. Are they constantly moving? Okay. She said the little molecules will spread out. This is the phase of matter where the particles are moving at the quickest energy, kinetic energy, at the quickest speed. Okay. Since they're constantly moving, they're actually not attracted or repelled to each other. Okay, when you watched that diagram a second ago, did all of the gases come together like a magnet and sit in the bottom corner?
Well, whenever you made it cold.
Well, when you put the pressure on it, you're right. But in general, no. A gas is just, they're not going to be attracted. They're not going to all clump together. They're going to be constantly randomly moving. They're not attracted or repelled by each other. Do you agree? Okay. Two more. Ooh, low density. That's a good one. That's not actually on the kinetic molecular theory, but you are correct about that. All right. This next one is something called an elastic collision. Okay. Is it possible for them to bump into each other? Yes. But when they bump into each other, do they stop moving or do they just continue? Do they bounce right off and continue moving?
It's like one of Newton's laws.
It is Newton's law. You're exactly right. Okay. They obey Newton's law, which means that a collision doesn't stop anything. They collide and continue to move constantly and randomly. Which means that you can't get them to stop just by bouncing them off of each other. Okay, so gases, another characteristic of gases is there are elastic collisions. They will bounce off of each other and continue moving as if nothing had happened. You okay with that? One more time, just going along with this idea that they're constantly in random motion and they're not attracted or repelled to each other. They just keep going. And then finally, the last one is what Christy said a second ago. What'd you say? Heat. Okay. Temperature is directly correlated to how much they move. Temperature is directly related to now there's a fancy science word for how much something moves. What's the fancy science word for movement? It's a certain type of energy. What's the energy of motion? There you go. You got it. Temperature is directly related to kinetic energy. So what the heck does that mean? If energy is really, really high, what can you also say about the temperature? It gets hotter. Okay. If the energy is really low, it's colder. Okay. So if I was going to do this like with my hands, I would say the hotter it gets, the more kinetic energy it has, right? What about the colder it gets? The what kinetic energy? The slower it is, okay? So temperature is directly related to kinetic energy. That means if temperature goes up, kinetic energy gets faster. If temperature goes down, kinetic energy what? goes down. Okay, do you want me to show it to you, or can you picture it again? All I did was when the flame was on there, they were fast, and when the ice was on there, they were slow. All right, exactly. So temperature is directly related to kinetic energy. Okay, 2 vocabulary words, diffusion and effusion. Does anybody have any perfume or cologne that they'll let me borrow? You really?
Patrick.
Oh, nice. Hey.
It's a long story. I don't want to tell it.
It's cool. It's cool if you're trying to impress the ladies with your axe. It's cool.
Are you impressed?
All right. I'm showing you a demonstration so that we can try to get some more of your 5 senses in there.
That is strong. You gotta like spin it. Spin
Do I? I'm nervous. What do I do? Spin it down? Okay. I'm nervous about this. All right, here we go. I hope I don't choke you guys out. Diffusion is the next thing, and diffusion is another characteristic of gases. And so I'm going to show diffusion by spraying this right here. Okay. All right. The point is I just sprayed this right here in the corner, which means I didn't spray it in your nose, but eventually, what happens?
It travels.
Okay, can you smell the axe yet?
No.
Can you smell it? Can you smell it? Can you smell it? Okay.
Can you smell it? Can you smell it now?
In a second, can you smell it now? Okay. In a second, I sprayed this in an area of high concentration, which means I put a whole bunch of gas molecules right here. Okay. Diffusion means they're going to go from right here. Where are they going to start to go?
I can smell it.
Spread everywhere. I can smell it. Okay. So because of a characteristic of the air that's in here right now, those molecules that used to be over here, can you smell it? Can you smell it? Not yet. Can you smell it? Okay. As Alex is like, oh my God. Did I spray too much?
Yeah.
Can you smell it, Christy? Can you, Lucas? Now you can.
It smells like that.
Okay.
Yeah, I can taste it.
In a second, it's going to diffuse across the whole room because of the unique characteristics of gases. Okay? Because of what we call diffusion, gas molecules will spread evenly. Okay? The key word there is evenly. Okay? It was in a high concentration in the corner. It doesn't want to be in a high concentration in the corner anymore. It wants to spread out evenly throughout the whole room. Okay, so the word diffusion means molecules will spread from an area of high concentration into the entire environment. And the way that we can remember that is we can always remember Patrick's axe. Okay, that's what diffusion means. And then finally, effusion. From this picture right here, this one is diffusion, this one is effusion, and now there's a little hole right here. What can gas molecules do if there's a hole there? Okay, so the word effusion means escape through tiny openings. And this is the reason that plants can give off the oxygen that we so desperately need. Okay, because the plants have very small openings, they go through their process, and gas can effuse through tiny openings and spread out. Okay, so diffusion just means to spread evenly. Effusion means that they have the ability to escape through tiny openings. All right, carrying on, this is pretty easy. Kinetic molecular theory, which is what we just did, goes through the ideal gas. All right, tell me one more time, what is the ideal gas? Ideally, what should a gas be doing? Okay. Okay, ideally the gases are going to be moving. Okay, which means that the temperature has to be pretty, yeah.
But gas still moves like in the winter, so.
You're right. Okay, which is what a real gas exists, which is what you're saying, but we're talking about the ideal gas. The ideal gas is going to be constantly moving. It's going to be a warm temperature environment. And what do you think is going to help it move more? Really tight pressure or nice open areas? Okay, which means that we're going to create a low pressure environment. Okay, this is how to create an ideal gas. Okay, we want it to be warm and we want there to be a low pressure on there, and that's going to enable these gases to move. But like Josh said, gases can also exist in any environment, but we just call the ideal environment a warmer temperature and a lower pressure. Are you okay with that? So, what's that?
Are you saying like all gas is in a warm temperature?
In order to make gas molecules act ideally, you want to give them a warm environment and take off the pressure. And that's the way that a gas will be most ideal. Now, can it be in any environment? Yes. But ideally, we want them, in order to get that to be the most ideal gas, we're going to put it in a warm temperature and take off the pressure. Okay? That's blah, blah, blah. That's just a definition. Okay, let's carry on. This is the last page of like the background information about what a good gas is. Okay? I'm going to introduce something to you called absolute zero. Actually, we're going to erase that. Okay. Introduce something called absolute zero, and that's called the Kelvin scale. Okay. From now on, we're going to consider temperature. Remember I told you that temperature is like kinetic energy? The hotter it is, the faster it moves. So from now on, we're going to use the kinetic energy scale, which is also called the Kelvin scale. Okay? And this taps on the idea of absolute zero, and that means absolutely zero movement. If you want absolutely zero if you want absolutely zero movement, do we have to put it in a cold place or a warm place? Okay, you're right. And not only does it have to be cold, it turns out that it has to be negative 273 degrees Celsius. Negative 273 degrees Celsius. Is that pretty cold? Okay, this is what we call the absolute zero. This is the coldest environment that a gas can be in when finally that particle will stop. You have to take that particle all the way to negative 273 degrees to finally get the kinetic energy to be zero.
So that way it turns into a solid?
Yeah, it's solid at that point. Okay? It's actually, I don't think that we've ever created absolute zero. Or at least the last time I checked, we hadn't. Maybe we've done it recently. No, even in outer space, there's still some motion in the particles. Particles have never come to a complete stop. But in theory, because of calculations, absolute zero would be negative 273. So that's where we start the Kelvin scale, and then we move up from there. Okay, so in an environment like this, 32 degrees Celsius, that's kind of like what you feel right now. 32 degrees Celsius would be, what's 32 plus 273? 305. Okay, so in this room right now, we have 305 on the Kelvin scale. Okay, the kinetic energy right here at 32 degrees Celsius is somewhere around 305 Kelvin, because I use this formula right here. Kelvin is equal to whatever the degree Celsius is plus 273. Okay, so you try. If you're in a 75 degree room, tell me what the kinetic energy of your temperature is. If you're in a 75 degree room, what's the temperature in Kelvin? Okay, you would take 75 and you would add it to 273 to put it onto the Kelvin scale. So it turns out that it's 3, 48?
That's a good
That's a good force.
fantastic force.
Oh, that was cute. I like superheroes. Is that right? Okay, so repeat after me. From now on, I will always turn it to Kelvin. Repeat after me. From now on, I will always turn it into Kelvin. Okay, from now on, I will always turn temperature into Kelvin. Okay, perfect. So I hope you know from now on you should be turning stuff into Kelvin. All right, that's a unit for temperature for gases. Now we're going to use some units for pressure. If you ever see ATM, that's a unit for pressure. If you ever see kPa, that's a unit for pressure. If you ever see TORR, which means torr, that's a unit for pressure.
It's not like something you find in Thor.
And if you ever see mmHg, that's also a unit for pressure.
Wait, is that
mmHg, which means millimeter of mercury. Hg on the periodic table is mercury. Okay, so this is background information. We're measuring temperature in Kelvin. We're measuring pressure in one of the four of these things. And finally, there's something that we call standard temperature and pressure. Standard temperature and pressure is just basically 273 Kelvin or 1 ATM. So if you ever are reading a problem and it says, what's going to be the pressure at standard pressure? What would the answer be? 1 atmosphere. If you're reading a question that says, what's the temperature at standard temperature? What is it? 273 Kelvin. Agreed? Are you guys with me? Okay, so like I said, background, background, background. Now we can finally start doing 2 quick math problems. Something called Dalton's law and something called the ideal gas law. Okay? Everything that I've described to you is just words and description. Now there's 2 math problems. Okay? Before we even get started, I figured this out last class, that these are awful examples. Okay? So we're not going to do those, but luckily there's one on your homework that actually relates to what we're talking about. Okay. The first thing, though, is Dalton's law. Go back to Dalton's law. And my question for you is, do you think that we have pressure on us right now?
Yes.
Absolutely. Okay. Do you also think there's more than just pure oxygen in this room?
Yes.
Okay. So there is pure oxygen in this room. What else is there in this room? There's nitrogen in this room. What else is there?
probably some methane.
Gross. Probably some methane. Do you guys know where methane comes from? Your digestive system.
Faucet is clearly.
Gross. He farted. Okay. We've got oxygen here, we got nitrogen in here, we have hydrogen in here, we have carbon dioxide in here because all of us are breathing. So there's a whole bunch of gases in this room. Do you agree? Okay. So the total pressure in this room is made up of a whole bunch of different gases, and that's easy. Okay. Dalton's law says the total pressure, which means whatever you feel, that pressure that you feel is made up of the sum. Now from math class, do you know what the sum means? You add them together, exactly. So the total pressure is just basically the sum of partial pressures. What? You said what?
You asked what's the sum is that equal.
Oh. That's funny. What does the word sum mean? Equal. All right, this one is really easy. Okay, so in your homework, since these two were really bad examples, go to your homework question number 16 and we'll just work this one out real quick. It doesn't get much easier than just adding things together. I know, that's because we don't have class tomorrow. So that's why I'm squeezing everything in today. All right. Number 16 on your homework says a mixture of oxygen, hydrogen, and nitrogen are exerted a total pressure of 278. Okay, so the total pressure is 278. Yep, number 16. A total pressure of 278. And then the next sentence says, if the partial pressures of oxygen and hydrogen are 112 and 101, respectively, then what's going to be the pressure of the nitrogen? Could you guys figure out what the nitrogen is going to be?
Wouldn't you just add up the two pressures they give you and subtract it from one?
Yes, exactly. Okay. The total pressure is 278. That's what you can feel. It's made up of 3 gases. So if one gas is this, the next gas is that, what would be the third one? Just add those two things together and subtract it from 278. Agreed?
65.
65 is the right answer. Yep. Okay, is that a pretty easy law?
Yeah. Yeah. You ate, man.
I was just saying, no, like, wait.
Oh, okay. I was like, what do you not understand? I don't know how to explain this any better. Okay, do you guys agree that the answer to number 16 is 65? Because of the law of partial pressures? Perfect. All right. This is the very last page. We are so almost done. The ideal gas law. Okay, before I write this down, I want to get this fresh in your mind again. Uh-huh. Okay. What are the things that matter?
Everything is matter except for energy.
What are the things that matter if we're talking about ideal gas laws? First of all, this matters. How much gas is there? Okay? How much gas is there is important. What else matters to change a gas? The what?
The temperature.
The temperature. Okay, so the temperature can change the way a gas moves. How much is there can change the way a gas moves. What else can change the way a gas moves? How much what is on it?
Pressure.
How much pressure is on it?
It's in the critical point.
Okay, so they're moving crazy because there's more pressure until finally it explodes. And then the last thing that can change it is how big the what is.
Okay.
How big the container is. Do you see that the gases moved differently when you changed the volume? Okay, and then, okay, so those are the things that we need to consider, and that's finally what the ideal gas law is. So right here. Okay. It's called the ideal gas law, but I like to call it PUV-NERT. 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 PV is equal to nRT. Okay, this is the ideal gas law. All of these are factors when we're talking about the ideal gas. No. Okay, pressure. Pressure is either going to be in atmospheres or kilopascals. Okay, what is V?
Volume.
And how do we measure volume? How do we measure volume? Okay, that'll give you how many liters of space that it takes up. The pressure will give you how many atmospheres it uses. N is going to stand for moles. That basically means how many particles are there, right? Okay, So if you only have one particle, that's very different than 2,000 particles, right? So the pressure matters, the volume matters, how much gas you have in there matters. R is a constant number, which means you're always going to plug in these things for R.
Doesn't R stand for rate?
You could think of it like that, because you're thinking about the kinetic energy. You can think about it like that.